왜 이랬지? 잠깐. Hello. I wonder if you can hear my voice. Can you hear my voice? Please let me know if you can hear my voice. Yes. Um, Today I have a little problem in, not little, I have a serious problem regarding my OBS. That's why today I cannot, I'm not able to show you, I'm not able to, the broadcast my lecture with my lecture note and my handwriting note as usual. I'd like to excuse you. I'd like to excuse me for this problem. I don't know why this problem happened today. So please report to my lecture note, and then it is inevitable to continue today's lecture by just announcing. Oh, now you can see my lecture note. Okay, it is not that bad. Hold on a second. Let me adjust the size of the screen. So today, so we have problem regarding my writing note page. Please excuse me for this problem. So anyway, it's okay to continue my lecture. I can deliver some most of information with my voice. Okay, so today I'd like to review what we did last time. So last time we discussed how to model the statically indeterminate structures, isn't it right? And then I introduce you two different kinds of approach. The first one is as given in our textbook, and the second approach is to use the procedure, the map that I provided you for the three conditions. So we use three conditions sequentially. For example, we use compatibility conditions, and then also next time we use constitutive equations, and then equilibrium conditions. And then as the last step, we check the boundary conditions. Then we can solve the problem, right? The procedure given in our textbook is so-called the displacement compatibility method. So-called in 우리말 the 변이 적합법. And the key point regarding the 변이 적합법 is superposition of the problems. So as long as we deal with linear elastic system, then we can superpose the response of individual lattices. So we can decompose the initial, our original structural system into different units. And then also we can decompose the boundary condition too. So after we finish, or after we superpose all the responses together, and then if you can satisfy the boundary conditions, then we can say that so we obtain the exact solution, because there exists only one solution. So as long as we satisfy the three conditions, isn't it right? The force equilibrium and compatibility and the constitutive equations. So if we have solution for individual systems satisfying all the three conditions, and then if you superpose all the results from the individual problems, and which satisfy the original boundary conditions, we can say that we have the solution. Okay, that's the key point regarding the displacement compatibility method. And then last time we discussed what's gonna happen. So if you introduce some thermal, not this one, sorry. So if you introduce thermal strains, okay, so I told you that we can superpose a strain. Okay, so the strain consists of many different sources. I mean, this is the total strain. The total strain is sum of many different strains. So I may start from 1 to say 10 or 20 or an infinite number of strains if you want to consider many different sources of strain. So typically our strain, don't trust, look at it. Actually this guy, this comment is very confusing, so don't look at this. Just listen to what I explain you. The strain, the total strain, this is a total strain. Total strain is equal to strain caused by the stress, okay? So I'd like to call this strain is mechanical strain. What I mean, that strain is caused by the stress development. And then plus other non-mechanical strain. So that's why last time that we called epsilon naught. Please understand the physical meaning of non-mechanical strain. So non-mechanical strain means that strain is not related to the stress in the current system. Do you know what I mean? Say last time I obtained a question from a student. Say the last time I gave an example of the pre-stressed concrete section. In the case of pre-stressed concrete sections, the tendons is stretched, isn't it right? Tendons is stretched in advance, and then the end of the stretched tendon is fastened to the end of concrete section. And that's how we introduce pre-stress to the concrete section, isn't it? So tendon is pre-stressed, and tendon is tendon is stretched in advance, and then the stretched tendon is fastened to concrete section. Well, it's not convenient because I cannot use my note today. Say we have concrete section, and then we prepare a tendon, and the tendon is stretched, okay, by an additional force. Additional pre-stressing force is stretched. So at the point of stretched, at the point that the tendon is stretched, the stress in the concrete is equal to 0 because the pre-stress is not transferred to concrete section. Only tendon is stretched. Okay, please make sure about that. And then, so we introduce a wedge here to fasten the pre-stressing tendon to the concrete part, and then we remove this force. Then what's going to happen? The tendon is already stretched, and then because we connect the end of the tendon to the concrete, and then the concrete becomes compressed. So now the stress of concrete becomes negative. The stress in tendon is still positive. And this is how we introduce pre-stress to the concrete section. So what's going to happen if we release this? So if you release this part, then what's going to happen? Then probably the length of tendon becomes shorter than the length of the concrete section, isn't it right? Because the tendon is stretched in advance. We just fasten the end of stretched tendon and the concrete section. That's why if you release the anchorage, we call that anchorage. This part we call that anchorage. So if you release this anchorage, okay, if you remove out this anchorage, and then tendon becomes free, and then the stress of tendon becomes equal to 0. So the tendon can deform freely, isn't it right? If tendon deform freely, the length of tendon becomes less than the original length of the structure. So that's why in the case of the pre-strain introduced to the pre-stressed concrete system the strain should be less than 0. Okay, you understand? Okay, the strain that we have to consider the compatibility condition is what? The total strain minus non-mechanical strain. Is it clear? So we calculate the stress by using the Hooke's law, the stress is equal to the elastic modulus, and then the total strain, please make sure this is really important, the strain is total strain minus non-mechanical strain, okay? So in the case of a thermal strain, the epsilon naught is equal to alpha delta T, okay? So if delta T is positive, what I mean temperature increases, then the strain increases too. Delta T is positive, strain is positive. In the case of pre-stressing technology, the epsilon naught is, as I told you, that represents shrinkage, isn't it? It's equal to minus some kind of, the pre-strain. Is it clear? Do you have any questions? Actually, this is my first time the OBS is not working as I expected today. So I don't know what causes this problem. By the way, this is duplicated. Let me try to remove this. Okay, now so I was able to remove duplicated slide. Do you have any question? Is the concept of non-mechanical strain clear? Any questions? So please let me know if you have questions. Actually, the comment regarding the thermal stress is rather confusing, Okay, the thermal stress is rather confusing. Actually, if you consider just free, statically determinate structure as given here, there is no thermal stress. Okay, there's no thermal stress. What I mean, because the material can deform freely as temperature changes. The material expand. Okay, it doesn't cause any stress inside. Okay, that's why this thermal stress delivers a little bit wrong information. So the thermal stress becomes important only when we have restrained structure like this. If the both ends are fixed and then the temperature increases, then what's going to happen? The stress is equal to the elastic modulus times strain minus thermal strain. So alpha, so delta T. So in this case, because both ends are restrained, the total strain should be equal to 0 because the total strain is subjected to the displacement compatibility condition. The displacement divided by the length, isn't it? So because both ends is fixed, that's why the displacement should be equal to 0. That's why the total strain should be equal to 0. So in this case, I have stress is equal to minus elastic modulus and then alpha delta T. Okay, then we have thermal stress. Okay, thermal stress. Is it clear? So in this case, we have negative thermal stress. So that's why here the magnitude, the alpha elastic modulus times alpha delta T means just magnitude of thermal stress. Actually, the sign of thermal stress depends on the constraint condition. And also the magnitude itself also depend on the boundary condition. As I told you, so if you consider statically determinate structures, then there's no thermal stress development, only the strain. Any questions? Is everything clear for you? So I'll fix this my note page during the break. But at this moment, let me continue my lecture without my handwriting. So I know the handwriting, my note writing would be very helpful for you guys to deliver the clear idea. But I don't know, it happened just before my broadcasting service today. So can I move to next subject? 원지우, can I move to next subject? How about 수민이? How about 민수? No response. 시윤이, okay, pre-strain이 non-mechanical strain. Yes, the pre-strain is a part of, is one of non-mechanical strain. Here, you need to understand the concept of non-mechanical very carefully. So non-mechanical means, that strain is not related to the stress development in the current system. That's the meaning of non-mechanical strain. So when we introduce, when we stretch the pre-stressing tendon, so we used, the external force, okay, not related to the current structural system. After we introduce or after we install the anchorage system at the end of the pre-stressed concrete member, then we eliminate, we remove the force required for stretching the pre-stressing tendon. That's why we say that that force or that strain, the pre-strain is one of non-mechanical strain. It is not related to the current force system. Okay. So how about other questions? And that strain was caused by another source of the force system, so not directly related to current stresses or current force system. Okay, so let's move to the next subject. So next subject is how we measure stresses on inclined section. Say, let's go back to the one-dimensional problem. Say I have a concentrated force here. So let's try to read the stress. For example, so if you read the traction on this surface, the traction means distributed force here. So we can read the distributed force very easily. How can we read this? So let's try to read the traction component. T is equal to what? The P divided the magnitude of load P divided by the cross-section area A. Okay, so to emphasize, I'm talking about the normal cross-sections. I'd like to say that A naught. Okay, so now let's consider this situation. So I'd like to read the traction on this inclined section. Okay, inclined section whose normal is inclined by angle theta with respect to the longitudinal axis of the member. Okay, so because we are familiar with Cartesian coordinate system, 직교좌표계, that's why we want to decompose the applied load into two different load components. One in the normal direction of the cross section, and the other one is in the tangential direction of the cross section. Is it clear? Okay, then how can we calculate the traction here? So the normal traction, the traction in the normal direction is what? The traction in the normal direction must be equal to the vector decomposition of the load P in theta direction. So we are going to call this normal force N, and divide by this cross section area, isn't it right? Because that force is distributed here. So A theta. And now how about traction in the tangential direction? So tangential direction is what? The magnitude in tangential direction is also very easy to calculate. The traction in the tangential direction is equal to the magnitude of the force in the tangential direction, V. V divided by A theta, inclined area. You understand? So to calculate these two quantities, what we have to do is we have to calculate the normal force component. So normal force component is given here. So it is very easy to obtain by using the trigonometric functions. So P times cosine theta is the normal force component. And the tangential component is P times sine theta. But how do you calculate this area? The area is what? What's the nature of area? This arbitrary area. Okay, so if you investigate the geometrical consideration, because if you define this angle is theta, and then this angle is also theta as well. Yeah, you agree? And then because of geometrical consideration, which means if you consider A theta times cosine theta, that means it's equal to A naught, the cross-sectional area in the normal direction. So we can explain A theta in terms of A naught and angle theta. Then how? So because I don't have enough space, let's move to here. The A theta is equal to A naught divided by cosine theta, isn't it? Okay, so we can plug in here. So if you plug in here, so we can calculate Tn, the traction in the normal direction. In our textbook, we call just sigma theta, normal stress in the theta direction. This is equal to what? P divided by the original cross-section area A naught, and then cosine squared theta. Is it clear, right? And please make sure that what is P divided by A naught? This is a reference traction. So last time we called just sigma, isn't it, right? So now to emphasize this original, the zero angle stress, normal stress, I want to call sigma naught. And this is equal to sigma naught cosine square theta. Okay? And then how do you calculate this? So in our textbook, we call tau theta. Tau theta. By similar consideration, tau theta is equal to sigma naught times cosine theta and then sine theta. You understand? Yeah? Any questions? So the result is given here. So the internal stress, internal traction depends on where we observe the stress, where we observe internal traction, depends on angle theta. Okay, so for example, so let's consider a material. Let's say first, let's consider concrete. So if you consider concrete, so concrete is pretty weak against tension. So typically we use the tensile strength to check the safety of concrete structure. And then how about let's consider steel. In the case of steel, we use so-called yield strength. Okay, but the steel, in the case of steel, the steel is in shear stress first. Okay, that's why if you measure the normal stress in different directions, then we have maximum normal stress when theta is equal to 0, because look at the magnitude of cosine theta. Cosine theta is equal to 0. Cosine theta is equal to 1 when theta is equal to 0, isn't it right? So it's maximum, which means if you consider this structure is made of concrete, then maybe we have failure in this direction, because on this surface we have maximum normal stress, isn't it right? My normal stress is equal to 0 on this direction, so that's why we don't have to check this direction. Okay, but if you consider steel, in the case of steel, usually the shear strength is more important. So usually if you consider the shear stress component, that becomes maximum when angle theta is 45 degrees, because it's combination of sine theta and cosine thetas. That's why we have to check this direction first. So we have shear band in the case of steel structures. Okay, and this is what I discussed you. So in the case of shear stress, it is maximum when angle theta is 45 degrees. So if you plug in 45 degrees here, sine 2 theta is sine 90. Okay, that's why the magnitude of shear stress is maximum. And then this is the conversion of cosine square into cosine 2 theta using the half angle theorem. And this is called half angle theorem, isn't it? In 우리말 반각 정리. And this is what I explained you just before. So the normal stress is changing. It is maximum when angle is theta, angle is equal to 0. And the shear stress is maximum in 45 degrees. Any questions? Okay, good student. Okay, now let's talk about the strain energy. Well, it's really pity to explain the strain energy. I really need my notepad to deliver the idea clearly. Okay, so now let's talk about the strain energy stuff. So before we talk about the strain energy, I need another consideration for strain energy. Okay, let's look at this. Before we discuss strain energy, look, we need to have what? We need to have energy conservation. This is the first law of thermodynamics, right? Then there are two laws of thermodynamics. The first one is energy conservation. The second law is what? The increase of entropy, isn't it? That's the thermodynamics. 훈이 왜 마이너스가 보이지? This is because of the direction. Look at this. So here, this is how we introduce a coordinate system. For example, how do I say? How can I explain you? Look at this. Look, because we choose this direction is positive for the shear stress. But if you look at here, by the way, look at this. This is sign convention. This is positive, isn't it right? This is a sign convention. So if you have inclined section, this is positive and positive. And then for the shear stress, and then this is the positive direction of shear stress. But it's heading downward, that's why we have minus sign. It's just a matter of the difference between the direction of the traction. Is it okay? Okay. So now we are talking about the energy conservation, isn't it, right? So according to the thermodynamics, the first law of thermodynamics is energy conservation. So energy, so if you look around our space, so we have many different sources of energy. For example, my energy is what? Is equal to, this is the energy unit, okay? The energy is, for example, because now I'm sitting in my office. So in my office I have electric energy, and then if I drop my pencil, so if I drop my pencil like this, so during this event, then I have potential energy, right? Potential energy, okay? And then, so if I deform my pencil like this, okay? If I deform my pencil, then it is also, there is a deformation energy too. So, and then to deform this pencil, so then I have to supply, my force, the energy of my finger, isn't it, right? My finger too. So we have many different sources of energies, okay? And these form the total energy. So according to the thermodynamics law, the change of total energy is equal to 0. Energy conservation should be equal to 0. So if some energy, if you consider a closed system, if one energy component increases, and that there exists at least one source of energy where its magnitude decreases, that's the energy conservation. So if you do not consider all the terms, so all the minor terms, so if you focus only the mechanical problem, then we have two different sources of energy. The first one is energy done by the external force. This is we call it external work. This is the energy, okay? So we use W because typically we call it work. Okay, we call it work. The energy done by the external force. This is external work. And then, so initially there is no deformation energy. But when we apply some deformation, then the external work is delivered or transformed into the form of deformation energy. Say we have deformation energy, let's say D, that forms the total energy. Okay, so any change in external work, should be equal to minus of deformation energy. Okay, that's why here I'd like to call this deformation energy conveniently internal energy. Okay, and then any change should be equal to 0. You understand? So if you apply an external force into a structural system, so we have change of external work, and this external work should be equal to the internal work. This is work conservation or the energy conservation. Then how do you define the external work? The external work is defined like this. The external work is equal to the work done by the external force. So obviously the forces are vectors. So it's a vector symbol with a bar. And then we consider dot product, the direction where the external forces do work, vector du. Now, typically make sure that the external forces are function of displacement, okay? So because we apply load very slowly, so we never apply the load suddenly. So what's going to happen if you apply load suddenly? If you apply load suddenly, wait a second. And let's look at this bubble. This bubble weighs 5 kilograms, okay? So this bubble is rather heavy. So if you apply this bubble into, this is my right hand, into my right hand suddenly, then what happened? Look at this. If you apply this bubble to my right hand suddenly, because of weight, oops, I have dynamic event, so I cannot resist, okay? The only way to apply this bubble to my right hand in a steady way is I have to apply this bubble very slowly, okay? Very slowly. And then some part of load is transferred to my right hand, and the remaining part is still supported by my left hand. That's how I can, transfer this 5 kilogram bubble to my right hand, okay? So in actual real problems, we never apply the load, a load to structural system in a sudden way. So we deliver the load very slowly. So this is a definition of external load, external work. And now how do you define the internal work? So internal work is equal to so work done by stress, okay? Work done by stress over the strain. And then this is we call energy density, deformation energy density. Is it clear? Deformation energy density. And the deformation energy density is defined if you have a structural body, mechanical system. The deformation energy density is defined at each material point. So because energy density is defined on each of the material point, to get total energy, so we have to integrate it over the volume of the structure. You understand? And then these two works should be equal to each other. The before we apply load and after we apply load. This is the work conservation argument. Any questions? Any questions? Here, let me take about 15 minutes break. During the break, I'd like to fix my OBS system. Yes, Jusung이, yes. The integration, the inside is deformation energy density. 시윤이, omega means the volume of the body, the volume of structural system. 동현이, actually, the pre-stressed concrete is very interesting. In these days, if you go outside and if you find any reinforced concrete structure look very slender, then you may think those structures are built in the pre-stressed concrete technology. Okay, as I told you, the concrete is strong in compression, but it's weak in tension. So as we introduce pre-stress into the concrete section, then initial stress is already negative, compressive. So if you consider a structure before we apply any load, then stress is free, isn't it? But in the case of pre-stressed concrete structures, the initial stress state is already negative, compressive stress, while the tendon is tensile. Then because the concrete is weak in tension, then we are able So now I have my notepad. So it almost got me. So can you see my notepad? Good. Actually, I was really embarrassed, you know. So when I run the broadcast system, it didn't work actually. But it's broken some point. Let me check. Let me try to have optimum performance. Okay, so now it's good. So let me continue then. So let me review what I argued, you know, so in today. So before this, before the second session of lecture, the first one is pre-stressing, isn't it, right? The strain superposition. Strain superposition. So let's talk about this. So look, so this is the condition that I like, the stress, and then strain, and the displacement. Okay, this is the flow of our analysis. And then please look at this. And then here, this section is called comparability. Okay, we call this comparability. And then this part, and this part is called what? Constitutive relation. Relation or law. Okay, let's call it law. Alright, so when you consider only the mechanical problem, we have the same strain. Okay, we don't have to worry about the choice of strain, but make sure that the comparability. So if you want to consider more than one strains, okay, if you have multiple strains, then the strain that we have to consider the comparability is what? For the comparability conditions, we have total strain. Here the red strain is total strain. The total strain is equal to the strain caused by the stress. This is the blue strain. And then the total strain is superposed by many non-mechanical strain here. So this is total. And then that's subjected to the comparability condition. Okay? And then that strain is caused by stress. Okay? That's why we put sigma by the constitutive law. Okay? That's how you may understand. So when you calculate stress, the stress is equal to the elastic modulus times the strain caused by the stress. That's the constitutive law. And this is equal to the elastic modulus and the total strain minus, so you can move this guy into the left hand side, non-mechanical strain. So once you understand this relation, then the calculation procedure is really straightforward. Look, here the epsilon non is non-mechanical strain. So this non-mechanical strain is given by an independent mechanisms. Like in the case of tensile, thermal strain, this is given by the alpha thermal expansion coefficient, and the temperature change. This is called thermal strain. And how about the pre-strain? If you consider tendon of pre-strain, this is equal to minus of the pre-strain of tendon. Here the epsilon p is pre-strain introduced to tendon. Do you have any questions? As I told you, here say we have concrete section. So initially we put a hole here. Let's say we have a hole. This is a concrete section. This is the front view of concrete section. We have initially hole, okay? And then we put pre-stressing tendon. Pre-stressing tendon. So pre-stressing tendon here. Then we stretch this pre-stressing tendon by a device, applying a certain force here. Then once this pre-stressing tendon is stretched, then we put an anchorage. Alright, so we put an anchorage. So once we have anchorage, once we install the anchorage and we remove this force, then what's going to happen? So this guy is stretched. The pre-stressing tendon is stretched. The epsilon, the strain is positive, and the stress is positive, isn't it right? And then because we introduce anchorage, and then this concrete is compressed, stress becomes negative. Which means once we introduce a pre-stressing force, pre-stressing strain to the pre-stressed concrete system, then before we apply any load to this structural system, the initial stress of my concrete is already negative. It starts, okay, strain and stress. This is a total stress strain diagram of concrete. Then initially, the initial point of concrete is already here. You understand? Because of this pre-stressing technology, it starts from the negative side of stress strain diagram. Then we can take advantage of, more margin in the tensile behavior. So if we do not use the pre-stressing technology, we start from the origin of stress-strain relation. So we have less margin, isn't it right? So the stress can be changed by this margin. That's why we introduce pre-stress to the concrete section. Who asked me the question? 동현이, is it enough for your question? If you still don't understand, let's do an example then. Okay, let's do an example. You don't need an example? So if you don't need example, then I don't have to do. Okay, good. So now let's talk about the strain energy stuff. The energy stuff. So as I told you, for any system, okay, we need to have energy conservation. Say, let's consider a system. So we have many different sources of energy. Total energy is, as I told you, the electrical energy. If I sit in my office, and if I play with my pencil, then to run this, to operate this pencil, I need to move my fingers, right? The energy introduced by my fingers. And then once I move my pencil in this position, then the pencil may have potential energy, isn't it? So if you consider a body moving subjected to gravity, so you may understand that there exists potential energy, isn't it right? So so-called m mass times gravity acceleration times the height, and the potential energy too. So typically we use the potential energy, let's say D. Yeah. And then if you do not consider any negligible energy change, then let's drop the electrical energy in my office. Then the change of energy change of energy during a certain event. Finger times, the change of energy in total system should be equal to 0, isn't it? That's the energy conservation. So look, let's consider my structural system. Say I have a structural system. Initially there is no load, okay? So but still there exists some certain energy. And then what are you gonna do? This is stage 1. And then in stage 2, so we wanna apply a load here. We wanna apply a small load. Very small load, okay? Very small load. And then in stage 3, so I want to increase the load, okay? Little bit and little bit. Little bit and little bit. And then finally, at stage, stage 5, for example. So we have terminal load. Let's say load P. So we have load F, okay? So finally, the F becomes P. F2, and the F3, and at F5 I have P. So because we have load, okay, so we have load, non-zero load, I may have end displacement U. So this part has own displacement. Also, if you measure displacement this point, there exists also non-zero displacement this point too, okay, in multiple positions, isn't it? So among all the displacement, we can measure displacement, at infinitely many points belonging to the structural body system, but only displacement along which the external load doesn't work is what? The end point, the load point displacement, isn't it? So here, during this event, okay, the change of the work done by the external force is what? We can calculate the external force is what? The work done by the external force. Integration of the force at each point over the displacement. Make sure that the force is changing, okay? So force is function of displacement. This is the external work. And how about the internal work? The internal work is equal to, so if you look at the material point, okay, at each material point we have stress sigma. Stress sigma, the work done by the stress sigma. The stress sigma is function of strain. And then it also work over the strain. Okay, over the strain. And that because this energy density, this guy is called the energy, deformation energy density. That represents the energy at each material point. So we have to measure the total energy, we have to collect all the energy density over the volume. Okay, here omega represents the volume of the structural system. Is it clear? So, because we are talking about the change of energy system during this event, so change of external energy should be equal to change of internal energy. So they are called, external work and the internal work. Okay? Any questions? Alright, so let's consider one-dimensional member. So if you consider one-dimensional member, So your internal work is equal to omega and the strain sigma epsilon d omega. In the case of one-dimensional member, how do you calculate d omega? D omega is area times dx, isn't it right? So this is equal to area times length integration 0 to L and then sigma epsilon dx. Is it clear, right? And then if you consider further the prismatic sections, then the stress and strain, especially the stress, is constant regardless the position of the material point in the longitudinal direction. That's why it is equal to area times the length of the member times the stress and strain d epsilon. Is it clear? Then how do you calculate stress? The stress, if you want to use Hooke's law, the stress is equal to elastic modulus times total strain minus a non-mechanical strain. So if you don't like to use a non-mechanical strain, it becomes simply elastic modulus times the strain. Is it clear, right? So let's consider this. This is equal to area times the length, and then now the elastic modulus is constant, we can take it out, times what? The strain, the epsilon, 0 to strain. So integration of this is what? The area times the length of the member, the elastic modulus, or half times strain square, isn't it? Now how do you calculate the strain? The strain is equal to the elongation of the member divided by the length. So let's plug in here. Then area times the length, elastic modulus times a half, length square, the elongation square. So it cancels, and this is equal to a half times L over elastic modulus times area, the delta square, delta times delta. What is this guy? What is this guy? Internal force, isn't it right? Internal force. This is equal to a half of internal force times elongation in the case of prismatic member. Okay, let's try to show the behavior between the internal force and the elongation. This is the internal force and the elongation. Because we are talking about a linear elastic system, the relation is straight line, isn't it? And then what is this slope? So internal force is equal to stiffness, EA divided by length times the elongation. This is called stiffness, isn't it right? The slope is EA divided by the elongation. Is it clear? And then the physical meaning of this, what? The physical meaning of this is integration. Integration of area under this curve. Just to take the integration area under this curve. Okay? And this is equal to, that area is equal to internal work. You understand? This is the internal work. And if you measure the relation between the force and the load point displacement, that is also equal to force and displacement. That would show the straight line too. So if you integrate the area under this curve, we call that external work. Do you understand the meaning of the external work and internal work and then energy conservation? And then let's revisit my diagram, this diagram. So we have force and then displacement, the stress and strain. Then if you consider the upper part, the integration of upper part, the force and endpoint displacement, that forms external work. And how about the lower part? Lower part, this forms internal work. Okay? Do you have any question? And then look at this. Here in our textbook, they say that the deformation energy, so another name of this internal work is deformation energy, U. Okay? So please make sure that the information given in our textbook is rather confusing. Just do not consider this. And this is a correct expression. This is deformation energy. And what our textbook says that the area in the upper part, this area, the authors are talking about this part. And then this part is called, so another name, it is equal to U star. The U is called deformation energy. U is called deformation energy. And then the U star, the upper part of this internal force and elongation diagram is called complementary deformation energy. Okay, and then also here same, and this part is called the external energy, external work. And also here we can we may interested in the upper part of this load displacement diagram. This is called complementary external work. Okay. Then if you ask me what is the difference, actually it looks the same. Yes, as given in our textbook. So if you put numbers here for P and the displacement, we have exactly same value. They are exactly same, okay? They are exactly same, but only for linear elastic system. U is equal to U star is only for linear elastic system. Is it clear? And also the external work is equal to complementary external work only for the linear elastic systems. then what's going to happen? So if you do not consider the linear elastic system, okay, let's consider general system. Let's say my stress strain diagram look like this. Let's consider this inelastic behavior. Then it is very obvious. The integrating normal stress becomes what? The internal force, isn't it right? The integrating strain becomes the elongation. That's why if you plot the normal stress, internal force as the consequence of integration stress over the cross section, and then the elongation delta is the consequence of strain over the length, and then this curve must be, the relation is not a straight line. It is obvious. So if you look at the area under the curve. If you look at the area under the curve, this is the area under the curve. Okay, oh sorry, this is the area under the curve, isn't it right? And then this curve, this area is called what? Deformation energy. And then make sure that this is functional relation. So this curve is defined by this displacement elongation, the function of elongation. And how about the area upper part? The area upper part is here. The area upper part is given like this. Okay? And then this area is called complementary deformation energy, U star. But look at this. On this side, it is controlled by internal force, N. So if you look at these quantities each other, and the control variables are different. In the case of deformation energy, the control variable is elongation. In the case of complementary energy, the control variable is internal force. So they are different physical quantities. So please make sure about it. And only for the linear elastic systems, these two quantities are the same. So we can interchange these two quantities each other only for the linear elastic system. Is it clear? And the for the external energy is the same. Okay. For the external energy, so P and the applied load P and the displacement, the lower part is called the external energy, external work. The upper part is complementary work. So if you add external work plus the complementary work, this is equal to the terminal load times displacement. And then the relation between the external work and the rectangular area PU and the complementary work is called Legendre transformation. Legendre transformation. So as you studied in applied mathematics class. Any questions? So now let's talk about how we calculate strain energy for this general problem. Let's go back here. So if you want to use shortcut, instead of going down to the material point, we can calculate the internal force and then elongation, isn't it? Because we already have the formula. The elongation is equal to length, elastic modulus, and cross-section area of internal force. This is kind of a shortcut. So we can exchange the information at this point here. Okay? So if you do that, we don't have to go down. So to calculate the internal work, we have to integrate, okay? But now we have a relation at the member level. Then we can sum. We can sum all the internal work for individual part. So we calculate the internal work for part 1, the AB segment, and then we calculate the the deformation energy for BC segment. That we can add these two energies together. So precisely speaking, what is given in our textbook is not correct. So U should be, equal to sum of, for the individual part of the member, or half of length, elastic modulus, and cross-section area, and then elongation square. This is the deformation energy. And then, as I told you, the complementary deformation energy is given by I is equal to 1 to, if we have multiple members, the half elastic modulus times area and L, the n square. By the way, we have ith member. Okay. So only for the linear elasticity, the U is equal to U star. That's why we can interchange this expression. Okay. So once we have the information of internal forces, then we can calculate deformation energy, the number of deformation energy. But make sure that deformation energy is controlled by elongation. The complementary energy is controlled by the internal force. Is it clear? Any questions? No questions? Okay. And then now let's talk about the maximum elongation of the bar. So now let's consider a system. So if you drop a mass, okay, let's consider the change of energy. As I told you, before and after any event, there should be no energy change. So look at this. Before we drop this mass, we had initial potential energy, right? Potential energy of the mass. Okay? And then if you drop this potential energy is transformed to kinetic energy plus, and then deformation energy. Because now we are using U, right? Sorry about it. We are using U. Deformation energy, okay? So precisely speaking, the potential energy of the mass is what? How do we measure this? This is mass times the gravity acceleration times the height, isn't it, right? So mass is given here. The mass is equal to m. And then we want to neglect the mass of the bar. Okay, let's neglect this. Let's neglect the mass of the bar. And then what else? And then the gravity acceleration is 9.81 meter per sec square. And how about the height? The height is initial height, right? The initial height plus, and then if you have any elongation, right? Any elongation. So elongation. So elongation is function of time, isn't it, right? The function of time. So it vibrates basically. So if you plot this elongation, so the elongation is equal to 0, and then we have the maximum elongation, and then maybe we have the vibration like this. Okay, or we may have elongation like this, delta initially equal to 0 and the maximum elongation, and this is 0 again. Okay, I don't know what's gonna be the minimum elongation before we calculate. Okay, so this is equal to mass times gravity times h plus delta. Okay, now how about the kinetic energy? Kinetic energy is what? How do you calculate kinetic energy? Kinetic energy is a half of mass times the velocity, isn't it, right? Vt. And how about deformation? How do you calculate deformation energy? Deformation energy is equal to a half of, right? Because we are interested in the elongation of this bar, right? The length L, the elastic modulus, and the cross-section area, and then the elongation square, isn't it? So if you check the velocity is because we are talking about dynamic problem. The velocity changes from 0 to the maximum value, isn't it? So we would have maximum elongation when the velocity is equal to 0. Okay, that's why if you are interested in only the maximum elongation, so we can take kinetic energy is equal to 0. You understand? So finally, the energy conservation is what? mg times h plus the maximum elongation is equal to a half elastic modulus times area and length and the maximum elongation. That's why we have this equation. Okay, so we can solve for this equation. So this is the answer for the maximum elongation. Any question? It's easy, right? This is energy consideration to calculate the elongation of the member. V square, where is it? V square kinetic energy. Here, delta. Ah, yes, you're right. Sorry about us. This is delta square kinetic energy. Sorry, the V square. Yes, you're right. Sumini, thank you. Sometimes, my hand become, work separated from my brain because this is afternoon. The sugar level in my brain is very low. 혈당이 부족해, 혈당이. Okay, then we can once we have elongation, then we can calculate the maximum stress, isn't it right? Because we want to use constitutive law. So always we are using the same relation. Look, so once I have elongation, then I can calculate the strain. The stress is calculated by the strain. The stress is equal to elastic modulus times strain, and then the strain is elongation divided by the length. So if you want to consider the maximum elongation, this is the maximum strain. The maximum strain and the maximum stress. This is equal to elastic modulus divided by the length and the maximum elongation. Is it clear? Alright, the next subject is advanced subject, so fatigue. Okay, now so far we discussed stationary or static system, isn't it? In the static system, so we assume that the load is fixed against time. But in reality, typically the load is changing. So let's consider the vehicle load. What I mean, a bridge subjected to vehicle loads. And because of the vehicle loads, the bridge vibrate, isn't it? It's subjected to the vibration or the change of the load. Okay, so load is changing by the time. So we can calculate the stress by subjected to the load. Say the load is changing. For example, let's consider one-dimensional member. So I have force F. The force typically the function of time. Okay, many times. So once I have the force value, I can calculate corresponding stress value. The stress is changing like this. So if the stress is less than the yield strength or the tensile strength value, so according to the discussion that we made so far, my structure should be safe, but in reality it is not. So if you repeat the loading many times, and then my structure will fail. The structure, the phenomena in which the structure fails by the stress less than the tensile strength limit, or compressive strength too, the strength limit, that we call it fatigue. Okay, fatigue. And this is the stress change range delta sigma. Typically we call S. So if you measure the the stress change level delta sigma, or S, by number of repetition, this is, for example, 1, 2, 3, 4, 5, blah blah blah, okay, then we can plot the number of repetition in the horizontal axis. So if you apply the high level of stress change, we have small number of repetition. Let's say the n is equal to 1000 times. If you consider, the small range of the stress change, obviously the number of repetition before failure would be longer, isn't it right? It should be big, like 1 million times. And then if you plot all this response until it fails, then typically it forms like this. It's a bilinear curve. Okay? And then this stress range is called endurance limit. If stress value is less than this endurance limit, then we consider there is no problem against the fatigue. So we call it fatigue. Okay? And this diagram is called SN diagram. in 우리말 SN 선도. Typically, the steel structures, design of steel structures, typically offshore. So offshore structures are subjected to wave loadings, isn't it right? Is governed by fatigue. And then the discussion about fatigue is a kind of advanced subject. So you may discuss fatigue in fracture mechanics class in graduate courses. So that's why today I'd like to introduce you to what's fatigue, and then let me skip it. And then the second one is Saint-Venant principle. Do you remember the last time I told you that there's no real concentrated load, okay? So if you apply the concentrated load, typically if you consider concentrated load, the load is applied over a very small area. Because of the consequence, the below of the load point, we have a high level of stress concentration here. But if you consider some of distance from the load point, and then that stress concentration is dissipated, eventually we have average stress value here. This is the Saint-Venant principle. When we design a structural member, we use this average stress distribution rather than talking about the stress concentration below the load point. Okay, so in this classroom for the mechanics of materials, we do not consider the load concentration below the load point. And this is called the Saint-Venant principle. So if you consider some distance from the node point, the stress distribution is almost uniform. Okay, this is Saint Venant principle. Next subject is stress concentration factor. So far, if you consider only the average or uniformly distributed stress here, so if you have a load here, because of Saint Venant principle, instead of talking about the high stress concentration here, we consider only the uniformly distributed stress here because of Saint Venant principle. Let's consider we have a hole here. Okay, so if you have a hole, then so we can assume that because of this hole, so we have this ligament. This is a ligament. Ligament means 우리말 붙어 있는 거. Ligament means 붙어 있는 거. So we can calculate the stress here. The uniform stress is what? The P divided by the area of the ligament. This stress is called nominal stress. 공칭 응력. Okay, 공칭 응력, nominal stress. But in reality, if you check closely, stress is not uniform. Near the hole, we have higher stress value, and the stress decreases by the distance from from this hole. The stress decreases. This is distribution of stress. Okay, and that phenomenon is called stress concentration. 응력 집중. We call it 응력 집중. So obviously stress is maximum here, isn't it right? The ratio between the maximum stress to the nominal stress is called stress concentration factor. We call it 응력 집중 계수. In abbreviation, we call it SCF, stress concentration factor. And this stress concentration factor is totally determined by the geometry. Okay, so it depends on the size of hole and then the size of the irregular cross section. For example, okay, in the case of flat bar with circular holes, that depends on the diameter of the hole and the width of the member. Okay, so we have different values. Say in the case of how do I say, for the infinite width of the member, we have maximum value of stress concentration 3. And then for the smaller sizes of bar, the stress concentration decreases. So it's determined by the geometry information. And then even for the bars with different cross sections. So in our examples, we considered only the abrupt changes of the cross sections. Okay, but this is just idealization. So we cannot use such kind of geometry for real engineering application. Instead of doing that, so we introduce a transition part of the cross section. Okay, with a certain radius. So because of this transition of the cross section, we have high stress concentration at these points. And that stress concentration depends on the radius of the transition zone. So these stress concentrations, there exists the stress concentration handbook. So usually we refer to this stress concentration handbooks to figure out the specific values of stress concentration for our geometry. Okay, so once we determine our geometry, so we have to look up the stress concentration handbook to determine the stress concentration factor. And then we calculate the nominal stress by usual approach. The nominal stress is equal to the internal force divided by the cross-section area. And then to determine the maximum stress, so we have to multiply the stress concentration factor kappa kappa to the nominal stress value. That's how we use stress concentration. Is it clear? Any questions? Is everything okay for you? Okay. How about nonlinear behavior? So far we discussed only the linear relations, the stress-strain relation. But even if you have nonlinear behavior, the principle is still same. Okay. So we consider the load and stress and strain and displacement. Okay, so we have nonlinear behavior only here, stress and strain. So in that case, for nonlinear materials, so we have to iterate. Okay, iterate for this nonlinear behavior. This is also advanced subject, so I'd like to skip it over. Okay, also even in our textbooks. So as a summary, we discussed the concept of the principal equations used for the structural analysis: force equilibrium, the compatibility, and then material laws. And then we discussed how to calculate the strain from the displacement. And then we discussed how to calculate stress from the internal forces, isn't it? And then we also discussed non-mechanical strain concepts and how we use non-mechanical strain to calculate the stress values. And then we discussed the effect of the change of the cross sections that produce so-called the stress concentration factors. And then we also discussed the internal stress depends on the observation directions. So if you observe internal stress in different directions, then we have different values because the normal stress value depends on the observation angle theta and the shear stress too. Alright, and then I'd like to finish this chapter. So here are your homeworks. Then make sure that your homeworks are due in, let me check, April 7th, okay? April 7th. So next subject is for torsion. Alright, chapter 3 is for torsion. So what you're gonna do in this chapter is so we're gonna study the concept of twisting mechanisms of circular bars, okay, and the hollow shaft. And then we're gonna study so-called torsional formula, and using the torsional formula we're gonna determine the shear stress in the member. And then we're going to discuss so-called torsion displacement relation. And then for torsional, in this torsional problem, so we're going to calculate both normal stress and shear stress development in arbitrary directions of the cross sections. And also here we're going to discuss why the elastic modulus is not independent of the shear modulus. Okay, we're going to discuss this. So here we have introduction, because the torsion problem is rather different from the uniaxially loaded members. So I want to stop my lecture here. So we'll discuss the subject of torsion next time. Before we finish our lecture, I'd like to have questions from you. Do you have any questions for today's subjects? No questions? 현민이, stress is on inclined section. Yes, obviously. Sure, absolutely. Look, 현민이, look at this. Say, okay, so I'd like to use a one-dimensional problem. And then it is subjected to concentrated load. So as I told you, there's no real concentrated load. So because we discussed Saint Venant principle, so obviously we have a high stress concentration here. But if you move a little bit far away from the load point, then we can consider uniformly distributed load. And then that stress, we calculate that stress by using this relation. So P divided by the cross-section area, A naught. Do you understand up to here? 현민이, you understand up to here? Good. Okay, so this is my structure. So to design this structure, we have determined what kind of materials that we have to use. For example, I can use concrete. So if we want to use concrete, the concrete is really we have to pay attention to the normal stress development, because the concrete is, the tensile strength of concrete is very smaller, much smaller than the tensile strength of concrete. So in this situation, we have tensile stress development. That's why we have to check what would be the maximum normal stress. So we have to make sure that my maximum the tensile stress is less than the tensile strength limit. This is really important. But in the case of steel, okay, the behavior of steel is typically governed by the shear strength. Okay, shear strength. Then if you do the test, if you apply tension to concrete, then the concrete member is cracked by the crack development. But in the case of steel bars, the shear band develops like this. Okay, it doesn't fail by the crack development. Of course, at very large strains, it failed by rupture. But before rupture, we have shear band development. So this is very important to check the shear stress development. So for steel, so we have to check if the shear stress is less than the shear strength of the material. 현민이, is it clear up to here? Good. So here on arbitrary cross section, So because we are using Cartesian coordinate system, so I want to check, each of normal stress and the shear stress is less than shear strength limit and less than the tensile or the compressive strength limit. That's what we want to do. And also we want to check this behavior in arbitrary direction. Also here we have normal stress and then the shear stress here, because we like to use a Cartesian coordinate system. That's the only reason that we do this job. And then to make sure the safety, the normal stress should be still less than the compressive strength or the tensile strength limit. And then the shear stress in that direction also should be less than any failure criterion. That's why we do this job. So the remaining point is how to calculate the normal stress component and shear stress component in this arbitrary direction, isn't it right? So let's define the direction of this cross section by this normal. And then we want to measure, the direction of the normal by angle theta with respect to longitudinal direction of the member. Okay? So if you understand the vector mechanism, we can decompose this force into two different force components. One is the normal part, and the other one is tangential part. So normal part is called N is P times cosine theta. The shear part is equal to P times sine theta. You understand? And then let's try to calculate the normal stress. The normal stress is what? The force acting in the normal direction. This is equal to N. And then we need to count this area, A theta. Alright, so let's consider geometrical relation. So this is angle theta 2, right? So we can calculate A theta very easily. The A theta is equal to A naught divided by cosine theta. Why? The projection of this area into that direction is equal to original area A naught. Isn't it? 그냥 정사형인 거죠? 정사형. 그치? So A theta cosine theta is equal to A naught. Okay? So this is equal to P cosine theta the A naught cosine theta. Then this is equal to P A naught cosine square theta. So P A naught is what? The reference normal stress value. Sigma naught cosine square theta. You understand, 현민이? Is it okay? And by the same logic, the tau theta is equal to V divided by A theta. And this is equal to P sine theta is here, the A naught cosine theta. That's why sigma naught cosine theta and sine theta. This is what happened. Look, say if we want to use concrete material, for example, then sigma theta must be less than or equal to the tensile strength value. Then we have to control sigma naught cosine square theta is less than the tensile strength limit, isn't it? The what would be the maximum value? Theta is equal to 0. If you put theta is equal to 0, then to guarantee the safety, sigma naught should be less than the tensile strength value. Okay? Okay, how about tau theta? if my material is sensitive to the shear stress development, then my shear stress should be less than the shear strength limit. Then let's plug in here. Then tau theta is what? Sigma naught cosine theta and sine theta should be less than the tensile strength limit. The shear strength limit. This value is maximum at theta is 45 degrees, square root 2, isn't it? Sigma naught 1 over square root 2. Am I right? Yeah. And the 1 over square root 2 f tau. Okay. That's why we can conclude that for this kind of material, my uniaxial stress should be less than 2 times shear strength limit. Does it make sense? That's why we are doing this job, okay? Because we are interested in the maximum values of the stress measurement. Our stress measurement depends on the observation directions, okay? So if you observe the stress values with respect to this plane, so we have different sets of normal stress and shear stress. Do you understand? Good. So let me stop my lecture here. See you next week.